Good morning, pandas, or afternoon, whenever you're watching this. We're going to do part 2 of our discussion today on um, polarity and electronegativity. So hopefully it will be a pretty simple lesson, and hopefully from yesterday you understand um, what a polar bond is, where there's an unequal sharing of those shared electrons, the shared electron pair of a covalent bond. So it's an unequal sharing. I'm going to start here with this periodic table. This is in the middle of the notes. The last one we did yesterday. And obviously, if you remember, the most electronegative element in the entire periodic table is fluorine, 4.0 Paulings. It's measured in a unit called Paulings, after the famous chemist Linus Pauling. So 4.0, that's the highest one. And obviously, if you remember, francium, way down there in the bottom left, is going to be your least, I guess, electronegative, and that's at 0.7 Paulings. So it increases going right and going up. Remember, the noble gases have 0 electronegativity. The ones with a higher electronegativity, they are more electrons are more attracted to them. So that's kind of how it goes. Trying to know these trends, it can help you out a lot when determining what kind of bond is formed. Is it polar? Is it nonpolar? Is it ionic? Now, to get really specific with this idea, we can actually do some math, very simple math, comparing those electronegativity values to each other, to the two elements or atoms that are in a bond. So in general, we already know that ionic bonds form when metals and nonmetals bond together. We know that from last chapter. Ionic bonds form when metals and nonmetals come together. Usually the difference between the two atoms and their electronegativity values is about 1.7 or above Pauling. So if you look at the two electronegativity values of the two atoms bonded together, and the difference between their electronegativity values is greater than 1.7, it's going to be an ionic bond. It's ionic. That's the bond character for that interaction. Covalent bonds form between nonmetals, as we know, two nonmetals. So they're going to have a different difference, I guess, of their electronegativities. The difference between polar covalent bonds is usually around, this is usually 0.1, maybe 0.2, all the way to 1.7. So if it's less than 1.7, the difference, so it's less of a difference. They're more similar to each other, the two values, between about 0.1 and 1.7. That's going to be a polar covalent bond because they're sharing. It's not ionic, but it's polar. It's unequal in their sharing. Now, what about nonpolar? Nonpolar, basically, is when you have, oops, this went away, sorry. Nonpolar is your really very similar electronegativity. So maybe two hydrogen atoms stuck together diatomically. Obviously, hydrogen is they're both going to have the same value. So you subtract one value from the same value, you get 0. So it's actually less than 0.1 even. So if it's extremely close, like 0 or 0.1, it's going to be a pure covalent bond or non-polar, or it's an equal sharing. Now, normally there's not a single bond that's purely, unless it's, maybe the same element. So we'll see some examples of that. So let's do a little bit of practice. This is a very simple thing. Let's say if we have sodium, and we have a bond between sodium and chlorine, and in parentheses, I put their electronegativity values. I looked up on a chart. Actually, I can show you what one of those kind of charts look like. It would look like this right here. I'm going to share this with you on Google Classroom. If you notice, it has like hydrogen's 2.1 right below the atomic weight. There is a value for the electronegativity. If you look at the key in the middle here, that's the electronegativity. Like fluorine here, the highest one is 4.0. Oxygen's 3.5. Carbon's 2.5. Sodium is 0.9. The first example we're going to use 0.9. Chlorine way over here on the right side is 3.0. So when we look at problems like this, you just look at a chart. You don't have to memorize them. 3.0 minus chlorine, you subtract sodium is 0.9. So the difference between these two parentheses numbers, difference between 3 and 0.9 is 2.1. Now 2.1 is over the magical number of 1.7. 1.7 is kind of the cutoff between ionic and covalent. So that is obviously 2.1 is obviously higher than 1.7. It's a greater difference in electronegativity. So that's ionic. Ionic are over 1.7. Oxygen and fluorine. Well, oxygen, if you look in the chart, is 3.5. Fluorine is 4.0, the highest electronegativity on the periodic table. Well, if you take the difference between 4.0 and 3.5, it's 0.5. Now, 0.5 is less than 1.7, so it's going to be a covalent. Actually, I should write on there, a polar covalent bond. It's actually a polar bond, polar covalent, because it's between 0.1 and 1.7. It's lower, the difference is. And finally, I just picked two that have the same exact electronegativity. Hydrogen is 2.1, and phosphorus is actually also 2.1. So obviously the difference between hydrogen 2.1 and phosphorus 2.1 is 0. If you subtract those two, it's going to be 0. That means it's still a covalent bond. It's a pure covalent bond. It's non-polar. They're equally sharing because both of them have the same attractiveness to electrons. They're going to equally share. So we can numerically figure these things out. If you ever have a bond, if you're looking at a structure and you want to know what type of bond that individual bond in a molecule is, you can actually look at their electronegativity difference. If it's over 1.7, ionic. Less than 1.7, higher than 0.1 maybe, it's going to be a polar covalent bond. So it's going to be polar, but covalent, sharing. And then if it's really similar, like 0, 0.1, it's going to be non-polar. Still covalent, but non-polar. So an equal sharing, not an unequal sharing like a polar bond would be. And we'll practice some of this today. So if you're, you can get some help with this. Now, okay, a dumb riddle, because it's my job as a chemistry teacher to tell dumb chemistry jokes. What's the name of 007's Eskimo cousin? Okay, you got bond. Polar bond. Okay, no, that's stupid. But obviously, in our case, polar does not mean cold, but you get the idea. Polar bonds, very important. An unequal sharing of electrons in a covalent bond. Yeah, if you got to explain it, it doesn't make much sense, does it? That's okay. So let's talk about molecules now. A molecule is when you have, a big structure. It's a compound. It's a covalent compound. There might be more than one bond, possibly. Can you have a polar molecule? Not just a polar bond between two atoms. Can the whole thing be polar? Let's find out. Polar molecule. Let's find out what we can do. So obviously, if you have all non-polar bonds, if everything's non-polar, it's always going to create a non-polar molecule. It's going to be non-polar. That molecule is going to have very equal sharing of electrons all throughout it. And there's one side of the molecule is not going to be more positive or negative than the other. The entire molecule we're talking about here, not just the bond. But if a molecule has polar bonds, it's still maybe non-polar. This is going to be the weird case. You would think, oh, there's a polar bond in there. The entire molecule must be polar. Not necessarily, as we're going to see. If the bonds, the dipoles, those arrows we talked about that point towards the more negative side, where the electrons are hanging out more on that bond, are symmetrically arranged around the molecule, it can actually cancel things out and balance out the entire molecule and make it act non-polar, where everything's equally shared. And it can be non-polar. So while you might have some polar bonds in your molecule, if it's symmetrically laid out because of the dipoles, because of the shape, it can maybe be a non-polar molecule. So an example, carbon dioxide, CO2. Carbon dioxide, which we're breathing out right now, hopefully, oxygen is the more electronegative element. Definitely is. And if you actually draw the structure, I'm not drawing the unshared pairs around the oxygen. I'm just going to draw it very simply like this. It is a linear structure, but there would be 6 additional dots around the oxygen. I know that. The actual dipoles will be drawn like this because I said oxygen is the more electronegative element. The electrons want to go towards that, making it more negative. So this bond, the arrow goes that way. This bond, even though it's a double bond, we can still do this. The arrow goes that way because that is where, while this double bond is a covalent bond, It's an unequal sharing. So those electrons are pushing a little bit closer to the oxygen on both sides. What do you look at this? If you're doing tug of war and one person's equally pulling this way and one's equally pulling that way, it's kind of going to cancel out and no one's going to move anywhere. And this actually creates a situation where it's a symmetrical thing where the dipoles are counteracting each other and basically makes this molecule, even though there are two polar bonds in it. This is a polar bond, unequal sharing, has a dipole. This is a polar bond, unequal sharing, has a dipole. Overall, the molecule is nonpolar. So we would say carbon dioxide is a nonpolar molecule, even though it has polar bonds, because of its shape, its structure. It's very important. That's why we learn all of this stuff we did before spring break. Now, if these dipoles are not symmetrical, the molecule will be a polar molecule. It has one end of the molecule. The entire structure is more positive or more negative than the other, possibly. For example, SO3. This is what the structure will look like. It's technically a trigonal or triangular planar molecule. And the dipoles will look like this because oxygen does have a higher electronegativity, if you look on the chart, than sulfur does, S. So the arrows would point towards the oxygen, towards the more electronegative atom. So if you look at this, look at those angles. Everything's 120 degrees. And if you would play tug of war this way, where there'd be three ropes, and the middle is they're tied together, and everyone's at an equal angle from each other, and everyone pulls with an equal force, you're not moving. The flag on the ropes, like in tug of war, is not moving. Same thing here. SO3 is technically non-polar, even though it has three polar bonds in it, because they balance each other out. The angles are equal, and everything's pulling out. That is a non-polar molecule, SO3, even though it has three polar bonds. So this one, though, SO2, look at this one. I'll go backwards a little bit. SO2, yes, the oxygen is still more electronegative than the sulfur, so you're still going to draw your dipoles that way. But look, there is nothing over here. There is nothing there. This is actually a bent molecule. Bent is the shape. Look how there's nothing over here. There's nothing pulling this way to the right. So all the electrons are kind of going towards the oxygen in these bonds, with making this a partial. Remember, this lowercase delta means partial, a partially negatively charged area. Or this area, then, since all the electrons are on the left side, this area is partially positive then, because all the electrons are on the other side. Very unbalanced. So this one truly has polar bonds, but also is a polar molecule. SO2 is a polar molecule because the dipoles don't balance. You really got to visualize this stuff to see how it's working out. So that's a polar molecule, and that will interact with the environment differently than a non-polar molecule. Imagine a molecule that has a negative and a positive side. It's going to interact with other things that have negative and positives in weird ways, because it's going to be attracted on one side to negative things. The other side is going to be attracted to positive things. While this SO3 over here, it's not as much, because everything's equal. There's no positive or negative side to it. That's why polar and non-polar things tend to not get along very well in the chemical universe, because they're not attracted to each other. Two polar things, like two SO2s, would love to be together, because one side of the SO2 is negative, the other side of the SO2 is positive. So if you have another SO2 molecule, they might stick together even a little bit, because obviously negatives and positives attract each other. So that's something that we can talk about later, and in biology class we'll talk about a lot. Let's just try one, and we'll be done. What is the electron pair geometry and molecular geometry of this one? So we're going to try to figure out basically the Lewis dot structure and the shape of CH3Cl. What are the bond angles? We'll figure that out a little bit, and then whether it's polar or non-polar. So CH3Cl. C has 4 valence electrons around it. H, there's 3 of them, 1 each. That's 3. Chlorine, there's 7. This is what we did before spring break. We need 14 valence electrons. So if we draw it, carbon in the middle, 3 H's, Cl with additional 6. That is the structure. That's what we would draw it as right there. Because if there's 14 dots there, that is what it looks like. That should be familiar from before spring break. Now, what's the, I guess, geometry here, since there are 4 sets of electrons around the carbon atom, the electron pair geometry must be, as we know, tetrahedral. That is a tetrahedral shape, 4 things around the central atom. So it looks sort of like this if you would draw it in space. Tetrahedral. Now, tetrahedral, the bond angle, you don't know this, but every angle between every one of these, you didn't have to memorize these, is 109 degrees. All of these are 109 degrees. Every single angle is 109 degrees. Now, what does that mean about polar and nonpolar? Well, let's think about this. Here's what it sort of looks like. Every one of these angles between these yellow things is 109 degrees. Well, these are the electronegativity values if you would look them up on the periodic table. Carbon's 2.5, hydrogen's 2.1, chlorine's 3.0. So if we draw the dipoles, if carbon is 2.5 and chlorine is 3.0, chlorine has a higher electronegativity than carbon, so the arrow goes towards chlorine. And the plus side, because the electrons are going towards that. So that's why it's positive here. The hydrogens are actually less than carbon, 2.1 versus 2.5. So their dipoles are going towards the carbon. If you look at this structure, all the electrons are kind of pointing upwards a little bit. This one here is going towards the chlorine, and these are pointing towards the carbon. It is not canceling each other out. It's not symmetrical at all. Everything's kind of pointing towards the carbon or up. So it's going to basically make all the electrons are on this side of the molecule, and not as many are down here by where the hydrogens are. So this is partially negative over here, partially positive over here. Overall, the whole thing's neutral. There's still the same number of protons as electrons. It's overall neutral. There's no charge. This CH3Cl has no charge. However, it does have an unequal sharing of these electrons it has, of its shared electrons. It's covalent. However, it's really going to be a polar molecule. It has to be polar because it's unequally shared. Not like CO2 where they cancel each other out one way, one with the other. This one's definitely weighted on one side because the arrows are all sort of pointing the same direction. The dipoles don't balance each other out. It has to be a polar molecule. So it acts like a polar molecule. It would not like to interact with nonpolar things in nature. So that's something that chemists would want to know. Okay, so okay, we're going to get to this last part with our lab, properties of ionic and covalent compounds. So we're going to save that last slide for when we do our lab. So I hope you enjoyed just the last slide on this lecture. And if you have any questions, let me know. Thanks. You guys have a great one.